Here, so the next speaker is Tyler Reid. And Dr. Tyler Reid is a co-founder and chief technical officer of Zona Space Systems, which is a startup focused on GNSS augmentation from low Earth orbit. Previously, he worked as a research engineer at Ford Motor Company, which you heard earlier, in localization and mapping for self-driving cars. He was also a software engineer at Google, a lecturer at Stanford University, where he co-taught the top course on GPS. He received his PhD and master's degree in aeroastro from Stanford, where he worked in our lab, and his bachelor in engineering, mechanical engineering from McGill. His thesis was made him recipient of the RTCA Jackson Award. With that, we'll welcome Tyler back to Stanford, at least virtually, and invite him to go ahead and present.
Thank you for the kind introduction and for the invitation to speak here today. We are truly grateful for the opportunity. I hope you all can see my screen and hear me all right. I always do a systems check. Yeah, very good.
Yes.
Today we'll be talking about commercial satellite navigation to support autonomy. To set the stage, we'll begin with some recent trends in aerospace as well as trends in navigation to give a sense of where we are and where we're going. We'll begin with some new drivers pushing navigation requirements to new levels. I think Sarah already alluded to some of this, particularly in the autonomous vehicle sector. This forms our motivation for a commercial satellite navigation layer from LEO, which is fast to evolve and which can meet the demands of these coming intelligent transportation systems. And I will conclude with an introduction to Zona Space Systems and our approach and plans for commercial LEO PNT. So I always like to start with this view, and those in the GPS lab have seen this plot before, but I like it so much, I like to bring it up every once in a while. And this is a view from 2016 of all the operational satellites in orbit. And to focus in on this, really this ball of string that we see here and see really what we have going on here, you can see some distinct groupings of satellites. You can see there's a group of folks out here in GEO. There's about 500 or so back in 2016. There's a group here in LEO. There's about 700-800 or so. There's not a whole lot in between, partly because of the radiation levels that were talked about this morning. But we do see our navigation constellations out here in MEO. In 2016, this was about 96 satellites or so. And what's interesting is that if you fast forward to today, so this is 4 years ago this November, to today, we have almost double the number of satellites that we saw back in 2016. And certainly there's been growth in each of these sectors. Of course, in navigation, we now see completed constellations from Beidou and also from Galileo as well. So very pleased to see that. But where we see the most growth really is in LEO, where there's almost 3 times as many satellites as there once was. And this movement is driven by several factors, which we will touch on later in this talk, but they include lower cost of launch to LEO from reusable rockets from places like SpaceX, as well as new techniques in just producing satellites. So for example, making them on assembly lines rather than making them for a specific mission. But these changes are fundamentally driven by an increased demand for connectivity. So you've probably seen in the news, SpaceX, OneWeb, Amazon, Telesat, and others are all building constellations of thousands or tens of thousands of satellites to provide global connectivity. And these have formed a new category of constellation, which they call the so-called mega constellations. And these represent the new space economy. SpaceX already has more than 700 of its satellites on orbit and has aspirations for 40,000 satellites. OneWeb has similar numbers in mind. But to understand the potential implications for navigation, I would like to look at the past to see where we might be going. And historically, new technologies and modes of transportation have brought new navigation challenges and resulted in many of the technologies we've seen to support them. And if we look at the past 100 years and how navigation systems have evolved, 100 years ago, maritime systems were making use of celestial navigation to give them kilometers level of position accuracy. Fast forward about 30 years from there, World War II, we see the advent of radio navigation to support emerging aviation activities, giving hundreds of meters of accuracy. 30 years later, we see the first satellite navigation systems to support the requirements of the Cold War. And of course, now we all enjoy meter level GPS location thanks to the satellite, or GNSS, I should say, thanks to the satellite navigation constellations. But the question is, what's next? And I've chosen this data point very carefully, partly because of the larger trend, but also because of some of the reasons that Sarah Houts mentioned earlier. But when we plot all of these on a given plot, and of course you can challenge this plot, it's never perfect, But if you look at the large trend in available location accuracy, you can see there is a very clear trend. There's almost a Moore's law of navigation, if you want to call it that. And we see that approximately every 30 years, there's a 10 times improvement in largely available location accuracy. It also suggests that every 30 years, there is investment in new infrastructure to provide new navigation services to support new needs. And what is that need today? Well, this is, as was alluded to by my previous colleague from Ford, Sarah Houts, autonomous driving is one of them. And of course, autonomous driving is just one of many applications that's looking for new navigation performance levels. But this is one that's near and dear to me from my previous work at Ford Motor Company. And as was mentioned earlier, part of why this is such a difficult problem is that it was determined that these vehicles, to do their job well, require 10 centimeter precision accuracy, 95%. So to give a reference here, 10 centimeters is about the width of the paint on the road. And of course, that's a difficult requirement in itself, but the hard part of this requirement is the requirements for safety. And of course, this is still developing, but the thinking seems to be that location needs to be known to the 30 centimeter protection level at the strictest standard in automotive, which for those who know this is Automotive Safety Integrity Level D, or ASIL D. But to understand where this is coming from, I'd like to dive a little bit deeper here and look at how is it that autonomous vehicles are put together in the first place. And there are essentially 5 steps to self-driving. There's the first step, which is localization, which is trying to answer the question, where am I in the world? This gives the first order context to start making decisions. Where are the roads? What are the rules of those roads around me? Next is perception. What are the active objects in that scene? So what are the other vehicles? What are the pedestrians that I need to be aware of to make decisions? Next is prediction. Where are all those objects going? This one's especially difficult today because humans are pretty unpredictable, as I think a lot of the community is starting to learn. Next is where should I go? So this is planning around those objects. And last, of course, is control. How do I get there? So what is the appropriate throttle, braking, or steering I need to do to execute that path? And in this process, localization really is the foundation. And along with maps, it provides the context to need the context to drive with confidence. But because it forms the foundation, it also has the strictest requirements, because failures in this stage tend to cascade to other systems. And this is in part where these strict requirements are coming from. So what is the target level of safety and autonomy? Well, as I mentioned earlier, this is still evolving, but being a form of transportation, it has been suggested that the long-term goal be set to the gold standard in transit today, which is civil aviation. And when you work out the equivalencies, this is a target of about one fatality per billion miles driven. But to translate that into requirements on the localization subsystem, and as Sarah mentioned, we did manage to release a paper of this from Ford Motor Company, so I do encourage you to take a look at that if you're interested in seeing the details. But to translate that into requirements on the localization subsystem, it means you're only allowed one failure every billion miles driven. And so what is a failure in this case? Well, for localization, the bounds of operation really are defined by the geometry of the problem. So that is, how big are cars and what are the size and shape of the road? And it turns out that if you balance those two things together, that the protection level you need for city driving, and of course it's different depending on the road you're on, but the strictest one is city driving. It turns out you need to know your position to better than 30 centimeters to keep yourself in that box. And so putting all this together, it means that for safe operation, the vehicle position must be within 30 centimeters of the true position, and that must fail less than once in a billion miles of driving. So this is a tough challenge. To put a billion miles in context, a billion miles is 250 times the entire US road network. And so that's every highway, every neighborhood road, every rural road, but it's also every snowstorm and every construction zone. And so really it is a tough challenge. And it's a challenge that we face as a community. And the reason this is so challenging is that the position protection levels are unprecedented. The level of safety is the standard in other modes of transportation, such as aviation, maritime, and rail. They're all fairly equivalent to each other, so the integrity levels are not foreign to us. But the degree of certainty you require in your position is at least an order of magnitude or more than what is achieved today. And so that really is the challenge. But how do self-driving cars localize in the first place? Well, here's an example of a self-driving Ford Fusion. I show the picture above because I've spent many hours in vehicles similar to this one, and so it's sort of nostalgic in a way. but they rely on sensors. And primarily in level 4 self-driving cars today, so the highest level of autonomy, these rely on LiDAR and 3D map matching for localization. Of course, other sensors are involved, such as inertial measurement units, 360-degree cameras around the vehicle, radar, ultrasonic sensors. Many of those are also used for object recognition and obstacle avoidance. And of course, GNSS is part of the mix as well. However, LiDAR really is still the king. And a lot of this choice has to do with the history of self-driving, going back all the way to the days of DARPA and some of the technologies that were adopted at that stage. But it also has to do with where these vehicles are operating, which today is in cities and typically in good weather locations. So cities tend to give sufficient 3D information for forming a position fix from map matching techniques. When you're in open flat areas, this is where GNSS works well, and it tends to be where LiDAR just doesn't have the sufficient information to give a good position fix. And in terms of weather, we see these vehicles operating pilot programs in places like California, particularly the Bay Area is usually a poster child for this. But we also see pilot programs in Arizona and Florida. And for those of you who were in Miami for ION GNSS a few years ago, you may have seen signs like this around the city, which is a sign of the times, I suppose, that these vehicles are becoming more integrated in our lives. But there's a reason these vehicles have been operating in these good weather areas, and really it's because it helps to bound the problem. And there are many challenges in general that remain with using these sensors to achieve the necessary safety. But when you add weather to the mix, it just makes the problem all the more difficult, especially when you're trying to use things like LiDAR, which are subject to absorption and scattering in bad weather conditions. And so one approach that's starting to emerge in the automotive industry to solving this problem is using redundancy. And to get to an ASIL D rated complete localization system, so everything together, you need multiple or multi-redundant, independent ASIL B systems. It's often decomposed this way. And so this means localization systems running in parallel with different failure modes. And generally speaking, there are two methods employed today. There is localization based on relative approaches. So this is using high resolution maps along with cameras and LiDAR and doing map matching. And there's the approach that relies on precision GNSS, which is often called the absolute localization approach. So this is just the jargon used by the industry. And so in general, satellite navigation works well in open skies, like on highways. So this is why we're seeing it being adopted for things like the Cadillac Super Cruise. We're seeing precise GNSS being used in that application. And this tends to be where LiDAR and computer vision struggles the most, just due to a lack of unique features in the scene. But likewise, sky obstructions which block GNSS signals are good targets for LiDAR and vision-based localization approaches. So in many ways, they are good complementary technologies. And certainly a lot of work has gone into both of these branches in solving this problem. But I'd like to focus, of course, on the GNSS side today. And so how do we get the absolute location branch down to an ASIL B level? And so let's begin with the challenges. Of course, you're all familiar with each of these, but just to touch on them here, you have challenges with atmospheric effects on the signal, and of course with satellite faults. There's challenges with availability, either from obstructions from buildings or trees, or from active sources of interference. And then of course there's multipath and signal reflections, and more there are just bad actors in the field with causing threats with spoofing. And on the last point, it was actually shown at this year's ION GNSS that with a relatively simple setup, you can spoof GNSS on driver assistance features that's already in production. So things like Tesla Autopilot, things of that nature. And you can steer the car into oncoming traffic and do some pretty dangerous things. And so it really is a growing concern out there in the autonomous driving community. And the state of the art of technology today seems to be focused on building better receivers and services, which overlay information to supplement the GNSS signals. So these are things like anti-jam technologies and other smarts on the receiver side, and of course, wide-scale correction services for improved precision. And these are good things. These are just great things that the autonomous vehicle community does appreciate. But how do we further address the last three items towards a very robust system? And so this is where I'd like to talk about the benefits of a low Earth orbiting system to complement GNSS. And one way you may pose this question, in asking the autonomous vehicle community is, what might you like to see in terms of enhancements on GNSS today Well, generally speaking, the three asks that I've seen are improved precision. So this is, of course, where we're seeing PPP and RTK come into the mix. Improved availability or resilience, so more signals and stronger signals and more of them. And then the last one is security, so seeing more encryption and then data authentication as part of that location service. And so one approach to bringing these features is with, of course, with a MEO GNSS backbone, is with an additional commercial LEO layer that can add a capability that can evolve quickly, perhaps on a 5-year timescale, to keep up with the pace of these evolving demands. So new LEO signals aren't bound by legacy, so they can have inclusion of things like encryption and data authentication, and of course other things as well. Being closer to Earth, they have the opportunity to provide stronger signals, so strengthening us to interference. And the last one is perhaps a more subtle point, but the fast motion across the sky leads to rapid geometry change, which is great for things like convergence of precise point positioning, as well as has some favorable characteristics for multipath. And so how do we do this? Well, of course, there's many ways. And certainly there has been news in the last year about interest in LEO PNT at the government level, particularly in the United Kingdom and in China. However, from a commercial service standpoint, it is enabled by the recent changes in aerospace. And a highly visible manifestation of these changes are the mega constellations under construction. And so one enabler is launch costs. So these have reduced by more than 10 times compared to 20 years ago, and is expected to continue to decrease as SpaceX starts to have more reused rockets in their arsenal. Another enabler is just mass production techniques for satellites and components. So to give a few examples here, OneWeb's production facility down in Florida is making 2 or more satellites per day. And SpaceX is launching 60 satellites at a time to LEO per launch. And so this is how they've gotten so quickly to 700 satellites. And to put these numbers in context, 60 satellites is the entire Iridium constellation, and 700 satellites just 4 years ago is half of all the operational Earth satellites. And so the result is that now we have highly available satellite platforms that are $500,000 or less to orbit. And of course, you do need more satellites in LEO to match the performance of GPS in MEO rather. It takes about 10 times more satellites, so you need about 300 satellites to get the same visibility or same geometry. But the economics represented on this slide indicate an interesting opportunity when you consider that recent numbers indicate that one GPS-3 satellite is closer to $500 million. And of course, these satellites have different missions and purposes, but it's an interesting opportunity nonetheless. And so this is where I'd like to talk about Zona Space Systems. So Zona was founded in 2019 by alumni of the Stanford Aeroastro Department. So this symposium really does feel like home to us, and it's really why it's such a pleasure to be here. And our mission is to enable intelligent transportation systems to operate safely in any environment to benefit everyone. And we are headquartered in San Mateo, so just near San Francisco Airport, so just down the street from where the symposium would have taken place. But we also have a presence in the UK and in Canada as well. And so today I'd like to thank the Zona co-founders and team members for all their efforts in helping me prepare these materials I presented here. And so from left to right, we have Ashish Goel, myself, Brian Chan, Brian Manning, Jeremy Martin, Andrew Nish, Adrian Perkins, Kaz Gunning, and Paul Tarantino. And our founders are coming from a combination of aerospace industry as well as from GNSS research, where combined they have put more than 50 vehicles in space. And our team today consists of around 17 members in total, and we're working towards our first 2 demonstration satellites. And our concept for these satellites is simple, and that is because we stand on the shoulders of giants. GNSS today represents more than $50 billion in public infrastructure, and so it makes sense for us to use it. And by leveraging the GNSS infrastructure above, we can greatly simplify our satellites while still providing an enhanced service to commercial users on the ground. And this concept is further enabled by the ecosystem, so the ecosystem of these mega constellations, where we can leverage the many launch services and just highly capable satellite buses and components that are being produced in volume. And that's not to say that the system cannot operate without GNSS. It is designed to, but at least initially not to the degree required to support intelligent transportation systems. So I just wanted to be clear about that distinction. And furthermore, there's just strength in numbers. And there are many benefits to a low-cost platform that can be manufactured and deployed quickly, where some operational capability can be achieved with just a handful of launches. and potentially be updated on a frequent basis as well. And as much as we have focused on autonomy here today, because GNSS touches so many industries, such as such a commercial PNT service can benefit many. And both of those shown here, as well as others that are on the horizon, especially with an ability to evolve quickly and meet new demands. But building such a system doesn't happen overnight, and so we have a staged rollout plan with different levels of service along the way. Phase 0 is happening next year, where we are working with the navigation payload for ground demonstration purposes. So you can think of this as satellite on a tower or satellite on the top of a building. And this is just to show the technology in certain demonstration environments. Phase 1 is 40 satellites, and this offers a one-in-view GNSS augmentation service targeted for population centers. Phase 2 is 70 satellites, so this offers a one-in-view global service, and it starts to provide full positioning service, but not everywhere or all of the time, but just starts to provide that. Phase 3 is 300 satellites, and this gives global GPS-level satellite visibility and geometry, and hence full positioning services that are precise and secure. And 300 satellites might sound like a lot, but when you compare this to, sorry, jumped on me there, it might sound like a lot, but comparing it to the tens of thousands of satellites that are planned, I think it helps to put this in perspective. And so I just want to give a big thanks to the organizers again. It's great to see the symposium happening this year in these interesting times. And big thanks to all of you listening in. We're grateful for the opportunity to be speaking with you rather. And if you'd like to learn more about our approach, we did have a paper at this year's ION IEEE plans, which unfortunately was canceled due to world events ongoing. But the paper itself is available at the QR code link that's there. And of course, we're very happy to chat offline as well. I know it's difficult in these sort of virtual conference situations, so please don't be shy to reach out to me by email. I hope my email is showing up there, but the slides will be available afterwards, so feel free to grab it from there as well. But yeah, I'd be very happy to take any questions. So thank you very much.
Thank you, Tyler. Looks like the questions are starting to roll in already. So your first question is, what is the Zona GNSS signal and how does it compare to the GPS waveform?
A good question. I'll say that due to ongoing discussions with, I guess, I'll say many US government agencies, we're unable to give specifics on that in a public forum due to some confidentiality there. We are very happy to discuss that more offline, but I would like to say that, yeah, we recognize the importance of that structure. So yeah, I'm very happy to talk about that offline.
I guess related and maybe a similar answer, but what is the Zona frequency and license status? Yeah,
no, very good question as well. So I'd like to say that we recognize the importance of spectrum and coordination very early on, and that was actually what we started with. And so before we started any engineering efforts, this was our first effort in terms of simulation and doing that coordination effort with various government bodies. And so a comment I'd like to make on that side is we're happy to discuss more details on that offline. But one comment is, in general, our philosophy is to improve the performance for the end user, and hence protecting GNSS spectrum is paramount to that.
Next question is, can you comment on how you achieve precise time and orbit data at the LEO?
Yes, so I'll start with the case where we are leveraging GNSS above. So of course, in doing that and doing precise orbit determination in LEO, you require precise GNSS orbit and clocks. And so it comes down to getting that data to the satellite. And so I'll say there are already commercial services in place from folks like from Fugro, et cetera, that are offering precise orbit determination as a service. So offering those corrections in situ and an ability to do sub 10 centimeter orbit determination and clock synchronization in that way. So that's the GNSS dependent way of doing it. And there are other ways of doing it as well, and but I'll leave it there for that question.
Okay, and the next question we have is, how much weighting, I guess, do you think will be for the GNSS side versus the other sensors, such as the LiDAR, going forward for autonomous vehicles?
Yeah, that's a great question. It's actually very interesting when you look at the history of where GNSS has ended up in that system. When I first entered the autonomous vehicle world, definitely the spirit of how do we combine these sensors was just, well, we don't care about anything else. LiDAR is king. Maybe we need an inertial measurement unit, but GNSS is so unreliable that we just don't use it. But it's funny because that thinking goes all the way back to the days of the DARPA Grand Challenges in 2004, when really it had only been a handful of years since selective availability had even been turned off. And one of the main teams at that event, which was relying on GNSS for at least part of their system, the Jumbotron that was not on the day before and was on that day was jamming GPS, and their system was not working. So it's some of the, I guess I'll say the views on how GNSS should be used go all the way back to experiences back in 2004. But of course, both of those fields have evolved substantially since that time. And I think that we're starting to see more and more reliance on GNSS in these self-driving systems, particularly in level 2 and level 3 systems, as they're sort of emerging on highways today, because it does offer such a ubiquitous and also low-cost solution. So how those two things will be weighted, I would imagine it's going to be environment dependent. And so most likely in city centers and places like that, the confidence in things like LiDAR will be higher compared to GNSS. However, in the case where you're in more open environments, whether it be rural areas or highway conditions, I would imagine the reliance on GNSS would be higher in those conditions. So I think the variability on that knob is going to be dependent on the conditions and the environment, is my guess.
All right, thank you. Next question is, will Zona help with indoor geolocation applications and achieve much needed sub-meter accuracy?
Yeah, absolutely. We're certainly open to having that as part of our roadmap, and we do have that. However, the satellite navigation system, we do recognize the limitations of penetrating inside of buildings and the kind of precision you'll be able to get through a wall and due to multipath and other factors. And so that we do recognize the limitations there. But on our long-term roadmap, certainly having that as part of our roadmap to improve indoor location is on there.
Next question comes from Sherman, which is, what are the deciding factors in determining your orbits? And given the recent news about near collisions, as well as 3% report that 3% of Starlink satellites are not controllable, is man-made space debris a major deciding factor in beyond just geometry concerns?
I'll say absolutely, and I think that more and more being a good citizen of low Earth orbit is going to be important, as so many folks are going to try to share it with so many satellites. And so I think we're seeing a few things there. One is that it's interesting that I think SpaceX's original plan had their satellites at much higher orbits, so 1,000 or 1,200 kilometers, but we're seeing their early runs being even at sub 500 kilometer altitudes. And I think it's partly because of reliability concerns, is my guess. I don't know, but as we're seeing 3% of these satellites not being responsive out of 700 is a fairly good sized number. And so making sure they come down in a way that sort of it doesn't have to be propulsively deorbited, at least for some of those early runs, seems to be important. On top of that, I think that so deorbiting concerns is definitely part of that. Just generally coordinating with others is going to be important as well. So if there are certain layers where there's about to be 40,000 satellites, for example, perhaps staying out of those is going to be important. But in addition to that, I'll say that there are, to support this new sort of ecosystem, there are many groups who are working towards technologies to deorbit some of these defunct satellites as a business. And so going up there and either sort of as a space tug, moving satellites around as they need to be done because they've due to a variety of problems or lack of propulsion, or deorbiting them as well because this is a shared space, and so being able to use it for generations is important.
I think this will be our final question because we do want to have time to have our remembrance for David Last. Will Zona be interoperable with 5G NR positioning?
It's a good question. The answer is we believe that is correct, yes. The aim is to be interoperable, yes.
Great. Well, Tyler, thank you very much. Always a pleasure to have you back, and obviously you're welcome back anytime. And for the time being, it'll be through Zoom, but when you are able to cross the border and want to, we'll be happy to have you back at Stanford.
Very good, thank you, Todd. And I'm in Canada, just so people understand the joke, I guess. Very good,
so,
thank you.
Yeah, and now I'd like